Awesome. All right, so formally welcome everybody to the thesis defense of Shengchen Felix Kao. So I wanted to start by just introducing the committee. Especially because we have two external members as well, so I thought it'll be great if we can also introduce them. So on Georgia Tech side, of course, I'm Tushar Krishna, I'm Felix's advisor, and we have Professor Callie Howe and Professor Vivek Sarkar. They were part of Felix's thesis proposal committee as well. So Vivek is, of course, an expert on compilers and programming languages. He's in the School of Computer Science, and Callie is an assistant professor in ECE. Her expertise is on HLS and FPGAs. And then again on Georgia Tech side, we have Professor Alexei Tumanov. He works on machine learning, especially systems for machine learning on the computer science side. And we have two external members, Vinay Subramaniam from Google and Anshuman Parashar from NVIDIA. Both of them have collaborated extensively with Felix during his PhD and have in fact shaped a lot of the artifacts and tools he's developed. So we thought it'll be great to have them formally be part of the committee as well and have one final go at poking him with questions. So Vinay and Anshu, can I request you to just briefly introduce yourselves? So Vinay, do you want to go ahead first? Yeah.
Sure. Hi, everyone. My name is Vinay Subramanian. I currently work at Google, part of the TPU architecture team. And it's been a great pleasure sort of working and collaborating with Felix over the last few years. And I'm looking forward to all the work that Felix has done over the course of his PhD as well.
Thanks, Vinay. Welcome. And Anshu? Yeah.
Hi, I'm Anshu from NVIDIA. I work on sparse and dense tensor algebra accelerators and tools to program them. And as Tushar said, we've had, both me and the rest of my group have had a lot of collaborations with Felix, and he's done a lot of good work.
Great, thanks, Anshu. So thanks everybody for taking out the time to serve on his committee. So just in terms of overall format and logistics, so this might be familiar to most of you, but especially for Vinay and Anshu. So the first part of the defense is completely open, public to everybody. Anybody can interrupt. Usually we encourage the other members, like other audiences, to just interrupt for clarification questions and leave like longer questions towards the end. But for the committee, you can feel free to interrupt at any time. Again, you can choose to hold on to your questions towards the end, or if you do want to ask in the middle, please go ahead and do that. So once the talk ends, and so Felix has targeted about 40-45 minutes for the talk, assuming no Q&A. Once that ends, we first open it up for questions to everybody who's attending. And after that, we ask everybody except the committee to drop off. And at that point, it'll just be Felix and us, and we'll have another round of Q&A and discussion with him. And at that point, we ask Felix to drop off, and then we have an internal discussion amongst the committee, primarily to decide whether we believe this work is good enough to to kind of be awarded a thesis, and B, if there's specific things the committee would like in the thesis document itself. So of course, Felix has already sent you the document. And if there's any specific pieces you would like to see in the document, that's something that you can let me know, and then I'll relay that feedback to Felix. Then we call him back and let him know the decision. So that's the overall formal process. So with that, we can get started. So again, it's my pleasure to to see Felix get to this stage. So Felix started with me 4 years ago. He came from NTU in Taiwan. And interestingly, he came with a lot of experience in, FPGAs and interconnects. And initially, in fact, his projects were around that space. But he was actually very interested in more of the algorithmic approaches as well, optimization, machine learning. And this was the time where, there was a growing interest in applying machine learning for systems rather than just, developing systems for ML. So he kind of, decided to look into that and went with it. So again, I'm not really an expert on that, so I do have to credit him for, really single-handedly developing a lot of the techniques that he'll talk about in his talk today. And since he's actually had a lot of, interesting research output, and we thought that it'll be nice if he can actually focus the defense more on some of the interesting insights that came out. So he's not going to go into all of his works, but he picked a few specific works where, he's going to try to identify some very, very interesting insights on how you should think about developing domain-aware optimization methods for designing new kinds of accelerators. So Felix, again, happy to see you at this stage, and the floor is all yours. Yeah.
Thank you, Anshu. And thank you, Anshu, for the introduction. And thank you, Felix, for the opportunity to speak. So, as Tushar said, I'm Felix. I'm a
Thank you, Trisha. Yeah. So today I'm going to share my thesis work, like domain-aware genetic algorithm for hardware mapping optimization for efficient DNA isolation. So first of all, I want to thank all of my committee members and also my collaborators and mentors in the industry and all the student collaborators. So DNA application are everywhere, as the quote from Andrew says, AI is the new electricity. So to run this DNN model with runtime energy efficiency, people start to build specialized hardware for it, which we call DNN accelerator. So why do we need them? Because DNN models are usually large, which often require millions of parameters, and it also infers lots of parallel computation. Second, it also introduces heavy data movement across memory hierarchy. To reduce the data, energy of data movement becomes one critical issue. So the need of parallel computation makes general purpose CPU inefficient, and the need of energy efficiency makes general purpose GPU inefficient. This is a template of a canonical DNN accelerator. First, it will house hundreds of thousands of parallel computing units, and also will use what we call data flow or mapping to map the DNN computation onto it. Here's a closer look at DNN accelerator. It will be made of first PE array. In each PE, there could be 1 to several ALU units. And also it will have hierarchical buffer like small local scratch pad beside each PE and shared global buffer and off-chip DRAM. And then we will have network on chip, NOC, to distribute and reduce data across the PE array. And these are the most higher order bit of the hardware resource configuration in the DNN accelerator. Then we will have mapping. So mapping includes several parts like tiling, ordering, parallelism, and shape, and we will go into detail them in the later slides. They form the map space. So the challenge of doing design space exploration in the DNN accelerator is the size. For example, DNN model has multiple layers. Here we only look at the per layer complexity. Just a simple example, if we give some choices in hardware, you can choose a number of PE, m number of buffer, then complexity just equal n. And also in the map space, we'll talk about their tile, order, parallelism, and shape different choices. So for a typical convolution layer with a constrained hardware resource base, the hardware could easily go to 10 to the 12 different choices, and mapping is 10 to the 24 different choices. So as you can see here, it's not amenable to do exhaustive search in this design space. So the goal of this thesis is to automate the framework for different stages of accelerator design. And this thesis demonstrates that designing searching algorithm with domain awareness can benefit map space exploration or design space exploration for DNN accelerator. So we propose an optimization loop for design or map space exploration for DNN accelerator. In this framework, we take in 3 inputs: DNN workload, objective, and accelerator configuration. Then the first step is to define the map space. Then we will develop or pick the cost model for evaluation. In this thesis, we use Maestro as our main cost model, and Maestro is an open source analytical DNN accelerator cost model. Next, we will design the searching algorithm, or we call mapper, to explore this search space. Then we run this optimization loop and finally get an optimized solution. So the optimized solution is a mapping for map search problem or a hardware design point for a hardware search problem. So for map space definition, we have a word called flexion, which is on formalism, the relationship between DNN accelerator flexibility to map space. We also have some work on mapper space. For example, gamma for GA-based mapper, and digamma for hardware and mapping co-exploration, and magma for mapper for multi-accelerator platform, and Confucius for DSE for hardware resource allocation. And finally, we have a work on MSE deep dive, which gives some analysis on the MSE and propose some technique to improve it. In this talk, we'll focus on these 3. I also have some experience on some other projects, like in E3, we are trying to deploy a neural evolution on FPGA and optimize it with hardware software co-design manner. And in flat, we are focusing on attention operation and accelerate it with data flow approach. And also have some work on ML model inside. In NetGain and AQGain, we use some quantization awareness and also use some technique like conditional gain. And in DNN Fuser, we use transformer for knowledge generalization on DNN mapping. So let's talk about the first part of our talk, flexion. First of all, let me describe let me share how we describe mapping. In this talk, we focus on intra-layer mapping, where interlayer mapping like fusion is not considered. For example, to express the mapping of a convolution 2D, and the mapping includes several axes. The first axis could be tile. So why tile is needed? Because it is not likely we can fit the whole tensor on the on-chip buffer. Therefore, we'll use some tiling to move partial of the tensor on chip. And the tile size decision will dictate how efficient we utilize the buffer in compute. And second is the order. So the order we fetch and execute the tile is also important because it will dictate which dimension we utilize the most. For example, they are weight stationary. Essentially, it means keeping the weight at the outer loop and reusing the weight. Third, we have loop parallelism. So we can choose to parallelize the compute across PE. Which dimension to parallelize across can dictate the PE utilization. Lastly, we have logical mapping shape, or we also call it level of tiling. It describes the number of tiling levels we use in this mapping, equal corresponding to the buffer hierarchy like L1, L2, L3 buffer and main memory. It also describes the logical shape of the compute unit, like the 2D PE array shape of 16x64. Finally, T for tiling, O for ordering, P for parallelism, and S for shape forms the 4 DNN mapping axis for DNN accelerator. Now, flexibility. So the flexibility of DNN accelerator means the hardware and software support for running diverse mapping for the same workload. So mapping flexibility is useful because there are diversity in DNN model, like there are different layer sizes, shapes, and type of computation. And also we have stepwise, pointwise convolution. Also pruning also make the characteristic of the workload different. So essentially, if you have more flexibility in the hardware, will allow more possible mapping, and you will have higher chances to find an optimal mapping for it. However, flexibility comes with area and power cost. For example, for tiling. So one practical consideration is whether to use hard partition input weight output buffer or the soft partition one. So apparently soft partition will have more flexibility but also has higher complexity. Second, ordering. It will introduce configurable address generator to dictate the order of buffer fetching. For parallelism, we need some marks or some control logic alongside PE to control spatial temporal reduction. And for shape, we need some network on-chip design to support different ways of PE clustering. So apparently, these mapping axes are not free. Therefore, how to cleverly support them is an important question. So in this talk, we discuss two aspects. First, which axis is more critical to support than the other? And second, along each axis, do we fully support them or just partially support them to save some area and power cost? So as we discussed, there are TOPS mapping axes, and also to enable or not enable them, we can form 16 different classes of accelerator. For example, class 000 means that we have no flexibility, and class 111 here means that all the TOPS flexibility axes are supported. So different accelerators are picked to support different combination of the mapping axes because they have a different budget and also they target different workload. Next, along each axis, we can also fully support them, partially support them, or just have inflexibility, like to stick to one mapping. So the flexibility degree of them could be from 0 to 1. And we call this flexibility degree flexion. It means fraction of the supported map space. So formally, it is defined like this. It's the supported map space supported map space over the entire map space. Here we show an example of the map space of a layer in ResNet. Here the darker red means higher performance point, and we can observe there are multiple high performance regions which we circle in green. Now let's assume if we have a hardware with 0.5 flexion, then what it means could be like this. The yellow part is the supported 50% of the map space. Potentially, the supported map space might not be large enough to cover some of the high performance region. And larger flexion will enable us to have higher chance to cover some high performance region. and the performance of the supported region actually depends on the workload. However, if we support extreme case fully flexible, then we are always sure we can cover the best possible performance point. So increasing flexibility is important because it can make the hardware to be more future-proofing. It means that it can cope with more diverse of DNN models. So let's see some evaluation. So here's the hardware resource consideration of our modeling accelerator in this table. And we perform two sets of case studies. First is the discussion between fully flexible and partially flexible. And we evaluate using MNASnet workload and evaluate along each of the four mapping axes. In the second case study, we want to show how the flexibility can benefit the accelerator to cope with a more diverse model. We investigate a what-if scenario. So what if we added more flexibility into an AlexNet accelerator 80 years ago? How would it perform for the new DNN workload nowadays? So in terms of new DNN workload, we consider ResNet, MobileNet, MNASnet, which are essentially more recent convolution-based model, and also BERT, DLRN, and NCF, which are mostly composed of fully connected layers. So for the first case study, first of all, let me describe how we consider partially flexible accelerator. It means it supports some fixed combination of the mapping. For example, for the partially flexible tile accelerator, we consider equally hard partition input weight and output buffer. For the order, we only allow one type of order in each input weight and output stationary category. And for parallelism, we only allow channel parallelism or activation parallelism. For shape, we only allow the P array to be logically partitioned with a coarse granularity of 16 cross 16. Let's see the result. From this graph, you can see that tile flexibility is most impactful. We can the performance gain from the green bar to the blue bar is the most impactful across all different axes. So tile axis is the most impactful axis to support. And also from order and shape, we can observe that orange bar is almost as close as the green bar. It means that partially flexible on order and shape, which is orange bar, can give compatible performance to fully flexible one, which is the green bar. So this is the discussion of like fully flexible and partially flexible. Let's see our second case study.
Felix, one quick question. Can you remind me what is included in tile flexibility? Like what aspects, tile size, shape, any other aspects?
Yeah, so tile flexibility, like we call it like partially flexible, it means that like input weight output buffer is like they are like equally hard partition, and if they are fully flexible, then we can do like any size of like input weight and buffer as long as we fit into the soft partition buffer.
So it's basically tile size and tile shape for the tile for those input and output weights. Yeah. Okay.
Yes. Tile flexibility is the tile size of each of the dimension which forms the input weight and output.
And just to confirm, you're only considering rectangular tiles right now, right, in this work? And maybe for machine learning, that's good now. I mean, for your kernels. In general, in the literature, you can have tiles that look like polyhedral, parallelograms, diamond tiling, all of those things too.
Oh, yeah, got it. Yeah, so we only consider like rectangle tile.
Yeah. Okay. Thank you.
Thanks. Yeah, so for the second case study, we want to show how flexibility can help future proofing. We consider two types of accelerator consideration. First, AlexNet accelerator. It means an accelerator specialized for AlexNet. And also X model accelerator means accelerator specialized for X model. For example, MNASnet accelerator means an accelerator specialized for MNASnet. In this graph, we show normalized latency to run the DNN model, so the lower is the better. For example, the blue bar here in MNASnet means I take the exact AlexNet accelerator and directly run MNASnet on it without any tuning, so what is the performance? And the orange bar here means what if I completely redesign the accelerator to tailor for MNASnet? What is the best possible performance I can achieve? So apparently, the specialized accelerator design, the orange bar, can achieve better performance than directly using AlexNet accelerator, the blue bar. So next, if we group the model by convolution-based model and fully connected model, then we can see a clear trend of performance difference between them. An Allison accelerator as an accelerator originally tailored for a convolution model can perform relatively well across other convolution models as well. It is because there are some general mapping idea that is actually transferable between convolution model to another. For example, the Parisian dimension choices or like stationary choices, they are transferable, which we will come back later in this presentation. Now let's start to add some flexibility into the accelerator. For example, AlexNet T flex means what if we add T flexibility, tile flexibility into the accelerator when we are designing AlexNet accelerator back in 2014. First of all, given the buffer sizes, number of processing elements, these are the area codes of each flexibility axis. One thing we can notice is that the additional area codes is not that unaffordable if we amortize to the cost of the entire accelerator. Then in this graph, we can see that the orange bar is always the lowest in the convolution model. It means that adding tile flexibility can improve the performance the most in convolution model. However, we can also observe that tile flexibility is not that impactful for DLRM and NCF. It is because the performance is bottlenecked by suboptimal choices along other mapping axes like parallelism or shape. However, BERT can actually benefit somehow from the tile flexibility. The key difference is that language model usually has higher dimension tensor and has more chances to leverage the parallelism strategy tailored for convolution model. And we can see that parallelism and order flexibility is pretty helpful for DLRM and NCF. And it is because these models are so different from convolution model, so to have flexibility to make different choices on parallelism and order is essential. So parallelism and shape flexibility actually is impactful to be future-proof to new workloads.
So Felix, quick question
Yes.
here. When you consider DLRM, are you considering the embedding layers and the fully connected layers in concert here, or are these like some specific subset of layers?
Yeah, subset of layer. We didn't consider embedding layer.
Got it. Okay.
Yeah, thanks.
Hey, Felix, question
Yes.
about order flexibility. So order is basically the permutation, right? And
Yes.
you can really make bad choices when it comes to the permutation. So when you say that on a prior slide when you were talking about order flexibility not being important, that means the baked order must have been a good order, right? It's not. I think that's what the message is. As long as you pick a good order, beyond that, the flexibility is not that important.
Yeah, agree. Yeah, so that's the part idea mentioned. Yeah, so for the partially flexible one, we actually pick some good ordering input weight output station. So this almost covers some of the like maybe 80%, 50% of the map space of at the older side. So that's why partially flexible is very compatible to like fully flexible one.
Yeah, and so now the question, and so the intuition behind that is, it's as your workload shapes change, the stationarity kind of the performance portability of stationarity kind of ports over, right? A stationarity that was good for one workload is also going to be good for another workload.
Yeah.
But it's interesting that these now let's go to the new slide that you were showing. Yeah, for DLRM and NCF, order is actually mattering.
Yeah.
So what can you tell us more about what's happening? Why is it that the order now matters more than the other layers, than the other workloads?
Yeah, so let me think. So the key difference is that all of this is like 6-dimension convolution model, and these three are just like fully connected layers. So the workload is too different. Like I suspect like the order doesn't like work well for the order that work well for convolution doesn't work well directly in fully connected. That's maybe the reason.
Mm-hmm.
Could it be that convolutions have more reuse, so it's more forgiving on the flexibility dimension?
Yeah, I think it could be.
Yeah, sorry, I'm just hypothesizing. I'm not sure either.
Yeah, and yeah.
Yeah, it could be that the orders that were chosen for convolutions, when those orders just don't make sense for fully connected layers, and you need a different baked order. I'm also hypothesizing.
Yeah. Can I also ask, like, what is the batch size that you chose here for, let's say, DLRM or NCF, one of them?
Yeah, so for this is old experiment, like I chose batch size of 1. Like we didn't consider batch size batching.
Okay, yeah, so that might actually be another reason, because at low batch size, I mean, convolutions can still get reasonable reuse, but for fully connected layers, maybe you're not seeing as much reuse. So you need this dimension flexibility.
Yeah, I agree.
Felix, how are you getting the area overheads?
Oh, this area overhead is like we have shown some like how do we consider different like codes for different tile sector in the previous slide, and these are just based on that slide, based on that code model estimation, we have this kind of estimation of the area cost.
So it's from Maestro?
It's not directly from Maestro, but some of the parameter from Maestro, yes.
Okay.
Okay. Yeah, so I will go to the next slide. Yeah, so in this slide, I'm adding more flexibility into the AliceNet accelerator. So we do this experiment in a sensitive analysis manner. So we enable 3 out of 4 mapping axes to see how critical each mapping axis is. For example, AliceNet no T-flex means we support all the flexibility axes except the tile flexibility. And first of all, we also show a baseline like the green bar. The green bar is we enable all the mapping axes, which is the most flexible option, and we can have the best performance here. And we can observe that the orange bar and the yellow bar are the highest for one another model. It means that the accelerator is more sensitive to tile and parison mapping axes. And we can also observe that the gray bar is
clarified based on I think what Anshu had asked, right? So when you are not flexible on order here, like when you're only flexible on tile and parallelism here, what was the default order that you picked?
What's the default? It will be like weight stationary, like.
Okay, so so they're all weight stationary. But okay, got it. Yeah. Yeah, again, that might kind of again be related to that earlier question, right? So if you did not have weight stationary as the default order but something else, then I am not very sure if the insights would have been.
Yeah, now it makes sense, because if for fully connected layers there is no weight reuse. And so being stationary on weights doesn't give you any benefit. Does that make sense, Felix? Do you think that?
Yeah. Yes, it makes sense. Yeah.
Okay.
Yeah. Thanks. Okay. Yeah. The second point is that we can observe that the gray bar is almost as low as the green bar. So what it means that here in this experiment, order is less sensitive. Or to explain it in another way is that some proper combination of tile, parries, and shape mapping assets can compensate the lack of order flexibility in this experiment. So we can say that partially flexible accelerator can sometimes be competitive with fully flexible one. Here are some takeaways. First, the additional area cost of full flexibility is not as substantial when amortized to the cost of entire accelerator, and tile flexibility is the most critical. And parallelism and shape flexibility are important to be future-proof to unknown workload. And some proper combination of tile parallelism and shape flexibility can sometimes compensate the lack of order flexibility. And partially flexible accelerator with low area cost can sometimes achieve competitive performance to fully flexible one. So here we have studied the map space. So what's next? Actually, to exploit the performance of the map space, we need to have an efficient mapper. So here we introduce Gamma. So for Gamma, the problem formulation is like this. Given a model and accelerator, we want to find the optimal mapping. So the criteria of a good mapper, there are two. You need to have a good representation and also have a good searching algorithm. So the representation includes the decision of how do you encode the loop order? Do you encode it into integer value? How do you encode the level of tiling? Do you, at the start of the algorithm, you just instantiate a massive 6 level of tiling level, which is a huge design space, and let the algorithm to explore it. So these are the decisions we can make. For the search algorithm, you can choose from do you use supervised learning, reinforced learning, black box, or others. So let's describe Gamma. So first of all, representation. In Gamma, we use a series of values to encode the space, which we call gene for each of the value and genome for a series of values. And this is one level tiling and L1 mapper. We encode the computer order by how we order this dimension notation and encode the corresponding tile size below it. Then we use another gene to represent parallelism dimension. We also mentioned there are multiple tiling levels, so we handle this by concatenating two mappers. We have L2 mapper and L1 mapper here, and each mapper has its own tile size, own order, and own parallelism dimension. And there are some constraints like L1 tile size is smaller than L2 tile size. So this is a representation of Gamma. Let's see the algorithm side. So Gamma is a GA-based algorithm, so I will use 30 seconds to refresh our memory on GA. GA has evolution part and evaluation part. Evaluation part is essentially cost model. Evolution part is a search algorithm. At the start, you will initialize a population, and there are multiple individuals in a population. Each individual has multiple genes. Then we use some operator like crossover and mutation to perturb their genes. Evaluate them with cost model and select some good one as the parent of the next generation. And then start all over again. It iterates until the algorithm converges or reaching the runtime or sampling limit. And the key of sampling efficiency of Gamma comes from the customized operator. So let me introduce them. First, mutate tile. So in naive tile mutation, we might randomly sample a new value for a certain tile size. However, a bad mutation like this can kill the offspring because violating the resource constraints such as the buffer sizes. In Gamma, we apply local mutation, which only mutate to its neighbor so that we don't suddenly become invalid because of resource constraint, and we can still gradually approach optimal point. Second, mutate order. So we can do any permutation like this. However, random mutation breaks some good relative ordering, which means we always randomly guessing in the order, and randomly guessing is not sample efficient. In Gamma, we mutate the order by swapping the order of 2 dimensions. It preserves most of the relative order, and the order can still gradually approach some optimal. Then let's look at shape or level of tiling. So you can choose to instantiate the 6 level of tiling level, which create a huge design space at the start of the algorithm. However, it makes the searching algorithm very hard to actually approach and explore any insight. So in Gamma, we did it differently. We start from one level of tiling first and allow the algorithm itself to decide when to grow to second level and deeper level. The intuition of this design are two. First, we start from simple problem first and gradually increase the complexity of the problem. And second, you may notice we start from a high level of mapping like this green one first, and then go to the lower level mapping like the yellow one and the blue one. It could be analogy to we start from a lower resolution of mapping first and gradually to figure out a higher resolution mapping.
So Felix, how does Gamma decide this? Is that still just a random choice, or is there something intelligent there on how do you decide when to go from one level to 2 level?
It's random.
Okay. So, I mean, it is possible that like at the very next step, you suddenly go to a 2 level.
Yes.
Okay.
And Felix, and these levels, they correspond to hardware levels. Is that right or no? Is this completely?
Yeah, that's right.
Okay.
So in practice, that we will set like maybe hardware support like up to 3 level. Then we will just set a constraint that you can just up to 3 level. Then you need to stop.
Okay, so let's say the hardware has DRAM global buffer register files. So
Yep.
effectively, what you're doing is you're just searching for the optimal DRAM to global buffer mapping at the first stage.
Yes.
And then at some point you decide, okay, now I'm going to factor in the global buffer to register file mapping as well.
Yes, exactly.
And then at a later point you decide, okay, I'm going to start thinking about the register file to MAC unit data movement.
Yeah. Yes. Yeah. Thanks. Yeah. So in this operator, like when we are going from 1 level to 2 level, 2 level, 3 level, a potential implication in hardware could be like this: like we go from 1 level to 2, 1D parallelism, 2D parallelism, or to 2D parallelism, or 3D parallelism. Or another like implication could be what like Anshu just described, like different hierarchy of buffer. So
Actually,
we
maybe
have
on that, does that implication depend on the specific thing you're exploring? So if you're exploring tile sizes, is the implication what Anshu just said about this is the tile from DRAM to global buffer and so on? While if you're exploring, I don't know, the parallelism dimension, then it's the implication that you just showed. Is the implication different depending on the specific axis of flexibility, or?
yeah, they are explored parallelly, but like as you say, like yeah, tile will make more corresponding to the buffer hierarchy, and parallelism choices will more corresponding to the
To what we
parallelism
just showed
approach.
here, yeah. Parallelism and shape will kind of correspond to what you just showed here. Yeah.
Yeah.
Hmm.
Yeah, thanks. Yeah, so we have growing, so we have an opposite operator H, in which essentially like algorithm can also decide when maybe just go down from 3 level, 2 level, 2 level to 1 level. So here I have introduced the representation algorithm of the gamma, and let's see some evaluation results. Here we show a layer-wise performance on ResNet 18. So y-axis we show the latency performance, so the lower the better. And axis is a different layer of ResNet 18, and we show the performance of different algorithms. And the blue dot here is where gamma stands. Note that some of the algorithms didn't converge within the sampling budget that we give them. So here we show a table of how many times they didn't converge. And gamma can consistently find valid solutions across different scenarios. And moreover, gamma finds solution with 2 orders of magnitude better performance than the others. So this is gamma. Next, I'm going to jump to the next part, which is MSE deep dive. In this part, I will divide them into 2 parts. First, deep analysis of MSE, and second, we will discuss the challenge of MSE for the new complex DNN workload. For the first part, we want to answer 2 frequently encountered challenges. First, there are so many proposed mappers. Can we systematically categorize them and study them to know better when should we pick one over another? And second, we want to see how the mapper actually works, and we will use gamma for this deep dive analysis. So we have seen this optimization loop, and we are going to see more on the mapper part. So there are dozens of different mapper proposed, and we categorize them into 3 categories: random and gradient and feedback. For the random base, it is essentially heuristic. So it has the fastest time to acquire one sample, however with poor sample efficiency. So one representative or state-of-the-art work on this category is random prune, proposed by the time loop method author. Next, we categorize black box and reinforcement learning into the same category and call it feedback-based. They, in general, use a learning algorithm to interact with the course model to improve its sampling algorithm across time. Therefore, they have higher sampling efficiency. However, it is slow because they have a learning algorithm to optimize for, and also they need to interact with the course model. And we use gamma to represent this category. Next is the gradient base. essentially leveraging supervised learning to train a surrogate model to replace the coarse model. Thus, it can be fast because of avoiding the interaction with the coarse model, and more importantly, it can use the gradient update to search for the optimal mapping directly. However, the caveat is that the surrogate model can only perform as good as the training data. It needs to be tied to one or few accelerated configurations, and the state of the art is mind mapping.
So I just
Also,
wanted to interrupt
yes.
and just give some broader context to the committee. I think I know that, so as Felix had mentioned, so he had actually gone into a lot more detail in Gamma in his proposal. So that's why he didn't go into a lot of detail here. One feedback from the proposal itself was to kind of understand why Gamma works. And so that's kind of really like this next phase. But if you do want more details on Gamma, I'm sure Felix has backup slides in case some of the things he talks about, just for some context as to why we went very quickly to this. Yeah, thanks, Felix.
Yeah, thanks. And there are also some other methods that we didn't cover, like mixed integer programming or MCNC. So here we pick like 3 different algorithms out of 3 different type of category, like random proof, mind mapping, and Gamma, and compare their behavior. For the following few slides, we will base our discussion with evaluation results, so I will discuss the setup here. We consider 2 sets of accelerator configuration whose detail is here. And the difference is only that, so we have talked about like the surrogate model of the gradient-based method need to seen or be trained on some accelerator configuration. So the difference is accelerator A is a seen accelerator configuration, accelerator B is an unseen accelerator configuration for the surrogate model. And we consider 2 types of workload, convolution workload and gem workload. And here we target the objective, we use energy delay product. However, like other objective can also be used. Here we show the EDP converge curves to the number of samples. And you can observe quickly that the feedback-based and gradient-based, which is orange or green, performs better than random-based. So learning method like feedback-based and gradient-based can keep improving the quality of their sampling functions so they can achieve better performance. However, the caveat is that the runtime cost per sample is about 10 times higher for learning method than the random-based method. So if we plot EDP to walk clock time curve, then you will observe that these 3 methods didn't have like too much difference. It is because when time constraint is strictly tight, learning method cannot yet get adequate data to improve their sampling function. Therefore, the effect of high sampling efficiency does not show up at the early stage of optimization. Therefore, if your time constraint is really strictly tight, then random prune is a more cost-effective choice. As mentioned previously, gradient-based will be tied to one accelerator configuration. So in addition to accelerator A, we also tested on accelerator B, which is an unseen accelerator configuration. So as you can see here, gradient-based method didn't perform as well in accelerator B as they do in accelerator A configuration. However, this type of performance loss can actually be recovered if we do two steps. First, we need to collect new data from accelerator B, which need like 1 million to 5 million of new data points. And then you will retrain the surrogate model. And after these are done, then you can search on the accelerator B configuration, and then the performance can be recovered. So until now, we have shown some pros and cons of different like random-based, feedback-based, and gradient-based methods. So in the next few slides, I will go pick one of the mapper Gamma and have a deeper analysis. So Gamma has separate mutation operator for different mapping assets like mutate tile, mutate order, and mutate parallelism. Also, yeah, so here like blue, green, and orange curve means if we only support mutate tile only, mutate order only, and mutate parallelism only, so what's the performance? And in this graph, we can
quick question about the previous slide.
Yes.
So what is, do you have a sense for what mind mapping's typical retraining time is?
Retrain, I don't know.
Okay, but basically, is it if it's short, then you could plot another chart in which you retrain mind mappings. So your x-axis for mind mappings gets shifted, but then you start at a much better point. So you drop to you drop to a more optimal point much quicker.
Yeah.
But if it's really long in wall clock time relative to how much time these 5K samples takes, then it's pointless. Then you don't want to plot that on the same chart. That's what I was asking.
Yeah, so I think the bottleneck is not like the retraining time. Will not be the retraining time, because maybe it take maybe 1 to 2 hours. It can be fully retrained. But I think the bottleneck is actually collecting new data, because like you need like 1 million to 5 million new data. So I think that's more bottleneck part of like the retraining.
Okay, got it. Okay, so then actually, trying to accommodate that data collection and retraining as part of an overall wall clock cost, it doesn't make sense. I mean, so if you're using mind mappings, then you really want to pre-train a bunch of models for a set of architectures that you care about, and start from there, because otherwise you don't want retraining in the loop.
Yes. Yeah. Thanks.
Okay. Got it.
Yeah. So here in this graph, you can see that the blue curve, the mutation tile only can achieve the best performance. So this actually is consistent with the analysis earlier in the flexion discussion that mutation tile is the most impactful.
But just to again complete the picture, that you did have to assume some default values for the other genes, right? And so it again naturally depends on what. So what were the defaults there? Were they just random, or was it something that was still hand optimized?
Yeah. So for this specific experiment is random. So random, because like we have like population size in genetic algorithm. So we like maybe population size maybe 20, 100. So random means like we initialize by 20 different order, 20 different pairs.
I see. Okay, so maybe let me clarify. Let me see if I understood. So you're saying that you will randomly, like you have a population size of 20, so you have random like 20 different orders in those 20 candidate genomes.
Yeah.
And you are not going to mutate those, but you will still do crossovers. Hence, you will still keep changing the actual orders. Is that the idea? Like, what is the, or will the order just stay the same? Like in all experiments, is the loop order exactly the same, or does it still change, but not because of mutation, because of something else?
They will keep the same. So you will only have 20 different options of order across order evolution.
Okay, got it. And you'll just keep picking the best ones and like going to the next level and so on. But there's 20 fixed orders, but randomly chosen. Okay.
Yes.
Okay.
Thanks. So the special operator in genetic algorithm is actually crossover. So here we show how crossover actually help. Here we compare the performance of for gamma, like the orange curve, with all the operator enabled, and also the blue curve is the only crossover, and the green curve is gamma without crossover. And we also show a data point of standard GA. So first, standard GA performed the worst. So without a specialized mutation and crossover operator that we discussed in gamma, standard GA is not really comparable in terms of performance. And then second, we can see that the orange curve actually performed better than the green curve. It means that adding crossover ability is actually crucial to be more sample efficient and achieve better point. So the takeaway is that blending two high-performance mapping, which is what crossover is doing, can effectively create another high-performance mapping.
Felix, hold on. So you might have mentioned this already, but I'm still trying to internalize it. Standard GA is also doing crossover, right?
Yes.
But so what is it what kind of a crossover is standard GA doing that gamma is not doing, for example?
What type of crossover?
So is it just random bits that standard GA would be transplanting?
So what crossover in standard GA is that they will just pick like maybe a segment of the genes and then just swap them. And but like in this design space, that if we just randomly swap the genes for two parents, then maybe just create another like invalid mapping.
Yeah.
But in gamma, we take care of that.
Okay. So would you say that the crossover patterns in gamma are a subset of the crossover that standard GA would do?
Yes, exactly. Yes.
It's a subset. Okay. Okay. So you're basically improving crossover efficiency by limiting the set of allowable crossovers.
Yes.
Okay.
Yeah, thanks. So in the next part, I'm going to talk about like what MSE might, the challenge what MSE might face for the new complex DNA workload. First is the runtime of the MSE. Since we run MSE layer by layer of the DNA model, the runtime increases linearly with the number of layers. It becomes cumbersome when dealing with extremely large models. So at this end, we propose an improvement technique called warm start. It is motivated by two observations. First, the DNA workload has similarity, so the consecutive layer in the DNA model will have shape similarity, implying we might be able to reuse some of the mapping. And second, like we have studied in the flexion, some information of the mapping is transferable between similar type of workload, like convolution to convolution. And we found in the previous discussion that order and parallelism are the axes that are mostly transferable. So the key idea of the warm start is that when we are running MSE for multiple layers of DNA model, we initialize the MSE by the solution found for the previous layer. It works like this. It happens at the start of the MSE. It has two main functions, similarity check and mapping initializer. And the replay buffer store the previous solution we have found, for example, map1 and map2 for the workload 1 and workload 2. And when, when a new workload comes, it will go into the similarity check function. Then we will use editing distance to compare the similarity to the previous workload. And the editing distance here for to workload 1 and workload 2 is 1 and 3. So here we'll pick workload 1's mapping, which is map1. And map1 will go to the mapping initializer. And in mapping initializer, it will inherit order and parallelism and scale the tile size to match the shape of the current workload. Then we can go into the MSE. So as you can see here, that this is kind of like, this workflow is like a heuristic base, which is formed by our observation. So let's see how it performs. So here we show the convergence curve when mapping in search. So orange is default option and blue is the MSE with warm start. First, for the first layer of DNA model, like the first layer of VGG and first layer of convolution, warm start doesn't affect any performance at all. Like both orange curve and blue curve start with pretty random and bad point. However, for the later layer, we can observe that the blue curve start at a much better point, which helps it converge faster. We also show how it helps when we are doing MSE for the entire model, and warm start can reduce the time to converge by 3.3 times to 7.3 times when searching the entire model. The second challenge we want to discuss is sparsity. There are more and more pruning techniques developed to sparsify the model. However, there are few studies on how sparsity affects the MSE. So the motivation here is that there are more models that are proposed with weight sparsity. Thus, the optimal mapping for dense workloads still perform well in sparse workloads. So our experiment is designed as follows. First, we find optimal mapping for workload with different sparsity. For each of the workload density, we search for the optimal mapping and record its performance in the blue cell. So what it means is like this. When the workload has density of 0.5, we go search for the mapping and its performance of EDP performance is 4.9. When the workload is now 0.01 density, we search for the mapping again, and then its performance is like 1.6. Then we evaluate each found mapping by different sparsity level. For example, the mapping for density 1.0.
To clarify,
yes.
These numbers here are okay, EDP, right?
Yes, EDP, yes.
Got it.
Yeah, thanks.
Okay, so lower is better, right? That's kind of the metric you have to go for.
Yeah, lower is better, yes. Yeah, for example, for density 1.0, the mapping found the mapping found mapping has the EDP of like 3.7, and we use this exact mapping to test it again. What if the workload now becomes 0.5? What's the performance? Then it will be 1.0, and also we test it on 0.1, then it will be 8.0. So we do this to all the different 4 kinds of density.
Felix, quick question. So what's the assumed architectural support for sparsity in the underlying accelerator, or do you assume any over here?
Can you say the question again?
Does the underlying accelerator have any specific sparsity support here, or is there any assumption around that?
Oh, yeah, the assumption is like the accelerator is like fully flexible to support any kind of sparsity.
And will you talk about what exactly that means?
What?
What does it mean to be fully flex? Is it like a sigma? Is that the other paper from your group? Like, is that what fully flexible means? Are there some dimensions to that?
Let me see.
Because flexibility comes at some cost, right? Like either in terms of energy, in terms of delay, and so on. I was trying to understand if those are accounted for or these are independent.
Okay, yeah. So energy is accounted, but like here we show cycles. So like the overhead for sparsity, it's accounted for the energy part.
Okay.
Yeah, I should mention like this. We use like sparse loop, like the like maybe
Okay.
time loop for this. Yeah.
So,
Okay.
I'll just add a little more to
Yes. Thanks.
Felix's comment. So as he said, he uses sparse loop, and sparse loop has a grammar for describing the sparsity features of that an architecture supports at various levels of the hardware. And so there's a language that says, okay, this hardware supports compression of data at this level. This hardware supports gating of zero valued data at this level, and this hardware supports skipping, which is, you save cycles by not fetching zero valued data and not fetching, if you're doing an intersection, then the zero valued data from one tensor allows you to not fetch zero valued data from another tensor. So there's a grammar that describes these architectural attributes, and sparse loop says we will model, we will give you an accurate cost estimate, both in terms of energy and delay, given an architecture which has these capabilities. And so
Okay.
Felix is sort of using sparse loop as a black box that and trusts that it's doing the right kind of modeling for an architecture that have that support.
All right. Yeah. Thanks for the context.
Thank you. Yeah. Yeah, and also like for each of the row, we mark the best performance one, like the lower one, the lower EDP one with green text. So first, we can see that the green text actually overlap with the blue cell. What it means that is that the best performance always happens when we actually search a specific mapping for that density. So we can tell that MSE do need to consider sparsity if we want to pursue the best possible performance. And finally, in this case study here, we are actually considering weight sparsity because of model pruning. And actually, if we add sparsity consideration into the MSE, weight sparsity is easy to support such weight because like weight sparsity is fixed after the model is trained and pruned. However, what about like activation sparsity? So activation sparsity is a little bit different because they are dynamic. It naturally comes from the like ReLU or auto activation. If we really want to consider the sparsity in MSE, then we need to research a new mapping for each of the input, which is not practical. So here we have a technique called sparsity aware. The key idea is that to learn a mapping that can generalize across a range of sparsity level, it works as follows. First, it works at every evaluation phase. It has two functions which interact with the cost model. At evaluation phase, when a new mapping is proposed by the mapper, it will first go into a density imposer. Essentially, it ignores the actual sparsity level of the workload. It imposes different sparsity to the workload to see how this mapper performs under different sparsity. Then we'll have different performance evaluation. We score the mapping by the weighted sum of its performance on different sparsity level, and the mapping will be ranked and selected by this score. So again, this is a heuristic formed by our observation. Let's see how it performs. So Here we have a workload with input sparsity. And we follow the same experiment methodology in the previous few slides. First, in the sparsity aware, we specifically pick 5 different sparsity levels ranging from 1 to 0.1. And we find one fixed mapping. And for static density 1, the idea is the same as the weight sparsity experiment. We search a mapping specifically on one density level, and their performance is recorded in the blue cell. And also we mark the best performance one with green text. So you can observe that the green text overlap with the blue cell, which is consistent with the weight sparsity experiment. It means that we do need to different mapping for different activation sparsity. Next, we see how this mapping perform at other sparsity level. We can find that mapping found for a specific sparsity level perform poor for other sparsity level. Then let's see sparsity aware. So I want to reiterate it found one fixed mapping, and we test it across density from 1.0 to 0.05. So we can see that many green tests located at the first column. It means that it can achieve like to the best performance like across many sparsity density level. And note that it can perform just a little inferior or comparable to the static density one, which is specifically optimized for one density level. For example, at density level 1.0, sparsity aware at this density level achieve EDP of 2.40, and static density, which is specifically optimized for 1.0 density, achieve like 2.39. So you can see that sparsity aware is inferior, however, very close to the optimized one.
So I had one more question here. So just relating it back to your TOPS framework, or if there's a different grammar here, that's fine. Is there any particular dimension of parallelism or the map space that the sparsity aware one actually picks differently or is more sensitive to, right, compared to the dense one? So for example, the dense one picks a mapping strategy, and then you find that the tiling strategies is the one that's most different in the sparsity aware one, or it picks a slightly that's the one that's more sensitive on the sparsity aware one as well. And once you fix that, then it generalizes really well. Like, do you have any thoughts on like what is the sparsity aware one doing differently, or is there any particular dimension of the map space that is more sensitive to the sparsity, or is more resilient or robust across different sparsity levels? Just like you had the analysis for the tile order is what matters the most, or that's where you get the greatest performance differential. Even over here, like this particular dimension is what is quite important to effectively target different sparsity regimes.
Got it. Yeah, thanks. Yeah, so yeah, that's a good question, but I didn't take a like deeper look on what the actual mapping they found for different sparsity level. But yeah, but I think that's a very good question. Then maybe I can take a deeper look at this.
Yeah, no worries. Yeah, I was just curious. Thanks.
Thanks. Let me see. Yeah, so yeah, here like we can see that the sparsity aware found one fixed mapping that can perform generally well across a range of sparsity level from 1.0 to 0.01. And here I just want to mention we use this sparsity range because DNN workload sparsity range is in this range. And a good follow-up work is to see how this technique can perform on other types of workloads such as high-performance computing. So here are some takeaways. Like learning-based methods have higher sampling efficiency by constantly improving their sampling function. However, they have the higher work clock time to acquire one sample. Tile is the most critical. And MSE need to consider sparsity. And leveraging DNN workload similarity can bootstrap mapper from better points. To tackle dynamic sparsity in addition, it is possible to find a generic mapping which work well across a range of sparsity level. Next, I'm just going to briefly touch the other three.
I was going to say, Felix, in the interest of time, yeah, if I know these are just so go through these very, very quickly, and we can so that we have time for the Q&A at the end.
Yeah, this will be very quick. Thanks. Yeah, so for the first work, we are targeting hardware mapping co-exploration. So the problem formulation is like this. given model and chip area budget, want to find the optimal hardware and mapping together. So here we have a word called digamma, which essentially changes the representation and search algorithm of gamma, like by adding new genes and also adding new operator for hardware. And another work is on map space exploration for multi-accelerator platform. It means that accelerator have multiple sub-accelerator. And the problem is that given a set of workload, a multi-sub-accelerator platform optimize the mapping across the sub-accelerator. Here we use the same MSE framework, and the searching algorithm is Magma. The next work is that we want to do DSE for hardware resource allocation. The problem is like this. Given a model and assume a hard-coded mapping, we want to find the optimal hardware resource allocation. This scenario happened at hardware design time. For example, we have targeted model like ResNet. We have area power budget. I want to use an algorithm to figure out what's the best compute and buffer allocation. We propose Confucius, which is essentially a RL-based manner. It uses RL to find coarse-grained solution and use GA to do few iterations of fine-tuning. Do we want to skip this?
No, I think you can go through this quickly. I think these are some of your key conclusions, right? Yeah, just go through.
Yeah, okay.
Yeah.
So as you can see, like we have designed mapper for different problems, like across different workload. Yeah. So here we discuss some takeaway when we are designing the mapper. We discuss them in the notion of design space, agnostic and aware. So here are some general points. If the design space is unknown for you, then maybe some stuff from generalized model method like deep reinforcement learning can pretty much work well. And second is that if you can model your problem easily as a Markov decision process, then just use deep reinforcement learning. It's better than a black box. And third is that, so if your problem has high dimension, then deep RL work better than black box. And also, I want to remind us that actually standard GA is not that complex as gamma. You need to define every detail. Usually, you just need to tune few hyperparameters like mutation, crossover, and so on. And of course, this kind of algorithm is design space agnostic, so their challenge might be they have lower sampling efficiency. In this work, we show gamma. We show the effectiveness of customized domain-aware operator. Like crossover and mutation, we can like minor perturbation. We show that minor perturbation of each generation may help the convergence. And growing and aging can grow and shrink the search space dynamically. In diagamma, we show that understanding the correlation between hardware and mapping can help effectively prune the search space. For example, there are some correlation between buffer allocation and the tile size you need. Next, I will just show some future work and conclude this talk. First, so far we discussed the DNN layer as workload, which means we only consider intra-layer mapping. However, inter-layer mapping or confusion is another mapping asset can be added in the MSE. Second, so far we mostly discussed different types of convolution, fully connected, or jam, which are the most widely used operation in DNN nowadays. However, new DNN operations are being proposed, and they may expose new mapping assets. So the study on which operation to support and how to support them is an interesting direction. Third, in this talk, the aim is to keep increasing the efficiency of MSE, and we believe when MSE becomes more and more efficient, we could start to think about the possibility to include MSE into the neural architecture search process to enable mapping and neural architecture co-search. Conclusion. So we analyze the impact of DNN accelerator flexibility to its map space and to its performance. We develop a specialized mapper with high sampling efficiency. And we perform systematic analysis on different mapper and propose different methodology to provide explainability to the mapper. And we propose techniques to increase MSE speed and cope with dynamic sparsity to tackle new complexity and workload. Thank you.
Great, thank you, Felix. Let's first open the floor for questions to like anybody. As I said, like the committee will still have time for like a one-on-one with you in the closed door. So first I'll maybe ask for people who are not on the committee, if you have any questions, please go ahead.
Hi, this is Gonhwa. I have a quick question, Felix.
Yeah.
First of all, yeah, thank you for a great presentation and sharing your insights. It was really helpful. So my question is also related to the mappers. So you mentioned For example, if you use mind mapping, you might need to retrain the model for different accelerator configurations. So usually, if I understand correctly, ML perspective of solution for that kind of problem is you can embed the hardware configuration as the input feature as well, so that you can train somehow like general model, so that you don't have to worry about retraining for different configurations again and again. In that case, you can train one general model. Now you can amortize the training time because you don't have to search for, let's say, you don't have to retrain for new model for different configurations, right?
Yeah, okay, yeah, thanks for the question. Yeah, so you are absolutely correct. So that's actually what mind mapping do. So as you can, yeah, maybe I didn't mention in the detail, like, so as you can see, like mind mapping can work on one accelerator configuration, but can generalize across different workload. So that's what they do, like they train a generalized model that take in the some pattern of the workload, and then that model can generalize across workload. But like workload is easier to generalize, but like accelerator configuration, like because you can, they are so different, like you can make different choice of buffer hierarchy p number, so that's become more challenging for them to actually generalize across different accelerator configuration. But you are absolutely right.
Oh, I see. Yeah, that makes sense. Thank you for sharing.
Yeah, thanks.
Any more questions from the rest of the audience? If not, thank you, everybody. So we officially conclude the public part of the defense. Can I request everybody to drop off? And only the committee will stay to have a Q&A with Felix. So Felix, and I'll also request you to stop recording.
Oh, okay.
Professor, I had one last.
Oh, there's one more question. Go ahead, Abhimanyu. Yep.
So Felix, you mentioned that when you were searching the design space, you had like multiple opportunities.
Abhimanyu, we lost your audio.
Algorithm. Okay.
Yeah, we lost your audio. Can you repeat the question quickly? Yeah.
Yeah. So when you were presenting gamma at the beginning of the presentation, you said that there are multiple options to choose for exploring the design space. So why did you go ahead with genetic algorithm? What are the other options that can be chosen there?
Okay, yeah, thanks for the question. Yeah, so for the different algorithm, like we pick black box because of design space, like it's harder, like maybe reinforcement also makes sense, but it's harder to like model them as like a Markov decision process for mapping problems, as we say. So we pick black box, but under black box there are also other optimization methods that we can pick. But the challenge is that we want to pick a very, very light black box method, which like genetic algorithm, because like we have a very fast code model, and we want like algorithm time and like code model evaluation times to be like compatible, so that we can like have a very good like balanced optimization framework. Does that make sense?
Yeah.
Thanks.
Thanks. Okay.
Great, thank you. So yeah, now we can stop recording, and yeah, in the interest of time, we should move on to the closed door. I'm just making sure. Yeah, it's just the committee.